Good evening. So unfortunately, I had to make this pre-recorded session. Currently, I am in transit and probably on the plane right now. So I apologize for making this pre-recorded, but I hope you still will find it interesting enough and it will provide the didactic value that is required. In case there are any questions, I'm always happy to jump on the discussion board, go on an extra lesson. We can always schedule something on weekends. And I am happy to also discuss the pertinent those parts of the lecture that are not entirely clear in class when we see next time, which is, I believe, at one point beginning of October. In any case, visual displays of data is something that is quite visual anyway, so I think the screen essentially is quite a suitable tool to discuss these things, and I hope this will not create any lack of understanding. So let's look into what Norton and Heinzen want us to discuss. So visual display of data. So as you can imagine, and we have talked already now about histograms and dot plots and some of the first ways to graphically depict data. And so as you can imagine, so there are good uses and there are negative uses of visual displays of data. So obviously, something that is more descriptive in nature, like a histogram or a dot plot, or something that kind of just gives you a feel for the data and you can visually kind of characterize and kind of get an idea what the data looks like, is mainly going to be a good use of data, right? However, there are also negative uses because you can use graphs in a way that it's misleading a reader, particularly those readers that do not have the statistical understanding or that do not have the education to question whatever they're looking at. And partly, I see it as my reason to inform you and to teach you how to distinguish between that. Does it necessarily mean that it's easily possible? No, it's not. It's like even I can be misled, right? It's like it's hard. You're looking at what you're looking at, and you're drawing conclusion based on what you're looking at, but you can't really look behind the curtains with many forms of depictions. What just happens after a while, looking at different graphs and looking at data, you get a deeper understanding, and you gain understanding of what can be and what cannot be. And this is where you kind of distinguish between whether this is actual real insights or not real insights. So positive and negative uses, so it can accurately and succinctly present information, whereas on the other hand, it can reveal and conceal complicated data. And concealing is really mainly what the problem is in the context of negative uses. And so if we speak about positive use, so that's for example, a graph that pursues. So this used to be a graph that was prepared by Florence Nightingale in the 19th century, basically depicting the causes of death of various reasons in the population in the areas she was active at this point. So you basically, what you see here, and this is interesting to see, so you have during conflict, armed conflict, you have increases of battle wounds, which is not very surprising, right? It's quite logical that this only will happen in times of war, but then the war kind of stopped and the war commenced at one point here in July, in August, and then Crimea got conflict. I don't know the historical background, so forgive me that I can't give you more insights, at least not right now ad hoc. If you have more interest, I'd be happy to read up and give you more insight. But so right now I couldn't talk more about this than just purely to what I see. But you essentially see that here battle wounds are associating with armed conflicts, which here is indicated. Then also what you see the deaths from other causes than wounds in battle and from disease are increasing during the winter months, which is also quite characteristic because in the winter months, essentially, it's cold, particularly in these areas in Russia. It gets very, very cold, and for that very reason, people may have frozen to death, and there may have been other reasons. Then also, deaths from disease also increased during the winter months, which is also a dynamic which is kind of well known for various reasons. So this is a so-called honeycomb graph that kind of quite convincingly shows the dynamics over the period of 1 year. It's not necessarily the easiest to interpret. It really depends on what the purpose of this graph is. But here it's just really to emphasize the point that there are differences in the causes over time. The problem is also that graphs can also be used to mislead. And so it was done in this graph. And that's a little bit of a problem. So you, for example, here, you have Ithaca times showing in one graph violating 4 different rules of how they essentially try to lie. They try to convince the reader that college tuition is just ridiculously increased, whereas at the same time the ranking is decreased. So now you have a couple of problems. So this graph has been labeled as the most misleading graph ever published. And so whether it's really the most misleading graph ever published, that's subject to debate, but it's a misleading piece of evidence. So problem number 1. So we have different time periods, right? So these both end at 1999, because this is when this piece came out. Now it came in 2000 out, and that was the last data we had, 99. So this, the tuition graph begins at 65, whereas at the same time, this begins at 1989. So obviously there's already a mismatch in observation lengths, which doesn't make any sense to depict it that way. So number 1 rule, time series always have to be on the same x-axis scale, and they always have to be matching each other's time course. It doesn't make any sense in a different, right? That's kind of logical. Second problem, you have an ordinal and the scale observation compared on the y-axis. So if you consider this the x-axis and time is the x-axis, it's clear that the y-axis also needs to have some representation. So it's two different y data series. One is the tuition, one is the ranking. So the problem with the tuition is that tuition has increased to an extent we don't really know. So we don't know what the scale is, but it's definitely a continuous variable. It's a ratio variable, and it's basically, it has increased, but we don't know how much. Whereas in the meanwhile, the ranking, as we know, is an ordinal variable. So when you think of ranking, would you expect the ranking to be better when the value is high or when it's low? So it's actually goes in the opposite direction. Right? So essentially, you want the prime, you want the best ranking would be 1, so that would be lower. So it indicates that it's better. So it wouldn't be actually. If you look bluntly at this data, it would be bad if that would be a better ranking, and then the tuition increases is kind of logical kind of dynamic. But okay, good. Then we have a deceptive starting point on the y-axis. Well, obviously, because this is, we don't know where this started and we don't know where it's going. Same here. We don't know starting points, end points. We know nothing with the y-axis. It's absolutely pointless. And then we have a reversal of a blind meaning of up and down. So this is essentially what I meant before. So we don't know if the ranking got better, and this is actually higher rank by having a lower numerical value, then it's okay. If the ranking actually went down and one would actually be up there, then it's a whole different interpretation. So it doesn't make any sense what they're showing. And I hope that's clear for everybody. So it's a very big graph. So, but now this really opens up the conversation piece. So we talked about positive uses of graphs and negative uses of graphs. So positive uses, it's you get an overview, you get the real data, you really see what the data looks like. Negative uses is you can lie with graphs, and that's a problem. And I think introductory statistics that we're doing right now is really responsible to teach you how to spot lies in graphs. It's not necessarily the case that you will always be able to do that. Neither am I, neither is anybody to say with 100% of certainty that there's a lie involved in this graph, but some may to some extent contain lies. So if we're looking at the various lies that are out there, so we have, for example, here the bias scale lie. So bias scale, we have just seen an example. So no starting point on the y-axis, no starting point on the or no ending point on the y-axis. So these are already problems. So you have scaling that aims to skew the results. So an example could be using 3 positive roots out of 5 options. Yes, that's one example. Another example is the tuition costs compared to the ranking of universities. So there are various examples you could think of. It's also when you refer whenever you show 2 time series on the same graph referring to different y-axes, and you have this capability to do in Excel, for example, a y1 and y2, so one is on the left side, one on the right side, that already is kind of debatable. I don't like it much. I think it's better to do 2 separate graphs, but again, this is you see it quite often. So it's debatable to use this approach. Second approach is the sneaky sample lie. This is the sneaky sample lie is not necessarily something that is only characteristic for graphs. This is also something that you will see with any kind of analysis. So this is basically what is being labeled a selection bias or selection statistic. It acts as what is labeled a statistical collider in the world of epidemiology. And it essentially is that you only choose a subset of your population that essentially will essentially show a dynamic that is more in the favor of your research question and favors your alternative hypothesis. It's definitely it's problematic, very problematic on all levels in statistics as well as in graph generation. Then we have the interpolation lie. The interpolation lie assumes a value between 2 data points. So I hope you all know the difference between interpolation and extrapolation. So inter stands for everything that is between 2 points. Extra stands for something that is outside of those 2 points. So an interpolation are values in between 2 data points, whereas extrapolation is something that either precedes or follows data points that you actually have at hand. So let's say you have data for 1996 to 2002, and you're extrapolating something to 2025. This is essentially extrapolation, and this is always kind of debate. Interpolation would be something where you have 1996 and 2002 only, and you say like, yeah, 99 and 99, it actually was that value. May be true, may not be true, who knows? So this is inter and extrapolation, extra being outside. Then we have the inaccurate values lie, and this is basically scaling to distort the portions of the data. So you're trying to normalize, or you scale them in a different way to distort those parts of the data that essentially will skew your results. That also would include something like logarithmic transformations, a transformation in some way, normalization of some way, standardization of some way, that also will include the exclusion of outliers, or things that basically show that the portion of the data are actually different than they are. So we have now, and this is basically what I said before, but inter and extrapolation. So these crime rates were actually meant to reflect, so there was assumed that there was an overall decrease. Oh, sorry. So the point that is being made here on this graph, and this is what Norton and Heinzen state, so they have said that there was a claim that between 1986 and 2006, there was a decline in crime rates. And if you look only at 86, which is somewhere here, and 2006, which is here, that is actually true, right? There was a decrease from 1986 to 2006. Nobody speaks about this in between, right? And this is particularly in politics. You see these kind of augmentations quite often. So you basically go into an interpolation line, or you go in an extrapolation line, and you try to kind of distort insights to an extent that are favorable for you. Also, you need to kind of understand which one actually caused this increase, right? Because violent crime here, for example, and this is always important to understand what you're actually looking at. So violent crime, for example, has steadily increased here over these 44 years that are observed here. Whereas property crime is really carrying this whole this whole dynamic here. And personally, when you ask me, it's like I would rather have violent crime decrease than property crime, although both are terrible, right? But like principle, I'd rather live in an area where there's less violent crime than property crime. But yeah, again, this is a conversation piece. But this basically was the driver for this dynamic, and not violent crime. Violent crime has not changed at all. If anything, has increased. And this is here. This is an example for an distorted scale line. So you basically, what you see here, you're talking here about there was an increase in nurses. We recruited more nurses. Yes. So the Guardian reports we recruited more nurses. So essentially, there was from 2008 to 2011, there was an increase of 3,000 nurses, and from 2011 and 12 to 13, there was an increase of another 15,000. So the problem is that when you depict it in a way like that, it automatically makes the eye look at this as the substantially smaller estimate, whereas this looks like this tremendous increase. Obviously not true. Obviously misleading and creates bias in the wrong direction. So to be kept in mind. So, but enough about all the lights. So we have now talked about how you can look at things with a little bit of tainted classes, and this should really not be done, for obvious reasons. So as the next topic, we're going to talk about common types of graphs. So we're going to be talking about scatter plots, and for a very good reason, because scatter plots is really, next to histograms, like the second most important graph. Histograms allows you to really get a feel for the data and to really understand the dynamic and the distribution of your data in your data set. If you have a scatter plot, in addition, you see every single data point. Seeing every single data point allows for you to really have an idea what relationships are actually contained in this data. What is actually in this data and what can you actually read from this data. And so essentially it's graphs that depict the relation between two scale variables. So we have talked about it, right? They are continuous variables and they're scale variables. And showing two scale variables on a graph with each data point being shown, you can easily see linear relationships as well as non-linear relationships. What does this mean? What is a linear relationship? What is a non-linear relationship? So when thinking about athletic performance, I think we all agree, and I'm currently training for the marathon, actually. So I'm running the New York City Marathon in November. So what I've noticed is the more I run, the more I train, the better my performance gets. So for that very reason, athletic performance increases with hours of deliberative practice. So that means that there needs to be some form of an association. An association, commonly spoken, is that when you have an increase in practice, you will have an increase of athletic performance. So hours of practice is a scale variable, and hours of performance, athletic performance is also a scale variable. So there needs to be, or there's assumed to be, a positive relationship. And this positive relationship will essentially manifest when you plot each point. So each of these points is essentially one individual. So let's say this is a class of 20 students. Each of these points is one student that will essentially have improve in the individual performance from 0 to 10 with hours of deliberative practice. So, and now scatter plots are really allowing you to visually judge and to visually investigate these associations. So now this is the way how you would produce such a scatter plot. So you would organize the data by participant. You would label the horizontal x-axis with the independent variable names and possible values. You label the vertically y-axis with the dependent variable names, possible values, and you make a mark on the graph above each participant scores on both axes. You don't have to make the mark. So we are essentially doing the scatter plots now. So I'm going to go through the lecture, but we're going to do a scatter plot at the end of the lecture in Excel and R. And I will post codes and I will show you how to do that. So but this is as easy as could be, right? It's a very intuitive, kind of easy to make graph. And the scatter plots really can show you like either there's a relation between scale variables, and secondly, it can show you a linear relation. So this is a linear relation would essentially be, if we go now to this athletic performance, a linear relation would be a relationship where you can draw a line through and you can say, okay, so this is linearly increasing over hours of deliberative practice. A nonlinear relation means that the relation is best described by a line that breaks or curves in some way. And this is more like this graph, for example. You see, this is not really a linear relationship, but you still see nonlinear trends and associations. I will talk about this. Okay, nonlinear. So a line graph essentially is a graph that would be used to illustrate relation between two scale variables. So basically a scatter plot would be used to construct such a line of best fit. So you have a line of best fit like this, and you make a straight line through it. That essentially is a line graph. So that's your line of best fit. Whereas line graphs, where you mean to visualize y-axis changes in values over time, this would be this graph. But it doesn't necessarily have to be over time. So just because you have here two scale variables, that doesn't mean that it has to be a straight line. You can very well also fit a nonlinear line through this. And so it's not a line. It's a nonlinear. You can fit nonlinear functions through every data you're throwing at the computer, right? And that's not a problem at all. The interpretation gets more complicated because that function has then a certain shape and form. It's not a linear shape, but a linear function anymore. It becomes a nonlinear function. It becomes easier to, becomes harder to interpret, becomes harder to work with, harder to sell to reviewers and editors to get published. But yeah, it's essentially you can do it. You can include. But now, for the sake of showing it an introductory statistics course, I think it's good enough to talk about the time series plot. And a time series plot is basically where you have a y-axis that shows you some form of variable, and you show that over time, some form of time, whatever the time is. So here it's, for example, it's the duration of a day. So this is positive attitudes over the period of 1 day, and this negative attitude over the period of 1 day. So now you can already assume that there are going to be trends in there that are kind of comparable, right? So if you have a positive attitude at 5 in the morning, if you are up and you are on twittering, the probability that you have a positive attitude because you sleep less, you can't sleep, is quite low. And your negative attitude is quite high. But then on the other hand, you have like at 9 p.m. is like, yeah, slowly your positive attitude increases again because this is when you're working. So this is when you're up and you're in a good mood. It's like, so here you somewhere you come back from your morning run, you have your coffee and you're like in a good mood, and then you're really happy, particularly on Sundays, not so much on Mondays, but then you basically come home from work after like 6-7ish, and then your mood is improving. But then at one point you're still not sleeping at midnight, and then latest at 3 p.m. is like your negative attitude is like at the highest, 3 a.m. Your negative attitude is at the highest. So this is how you would read in these kind of time series plots. You look at certain time periods and you try to make sense of what you see, and you try additional dimensions in there, which the additional dimensions here is really the day. And that makes a lot of sense. It's interesting to interpret. Okay, and then we have bar graphs and Pareto charts. So bar graphs we have essentially seen already. Like we have seen the histogram. And I actually owe some of you a histogram. So I forget who inquired about histograms. There was actually a problem with the histogram in Excel, and I have yet seen what the problem was. Histograms in Excel is a rather unconventional kind of way of depicting data. Excel is not really a data. It's more like for bar graphs and these kind of graphs, Excel is okay. It's not the best kind of solution, but again, we'll talk about this one today. Okay, so the bar graph visually depicts data in which the independent variable is nominal or ordinal. So again, nominal or ordinal x-axis, dependent variable is scale. That means that the scatter plot that before was scale on the y, scale on the x, now suddenly is like scale on the y, but nominal or ordinal on the x. So now the Pareto chart is basically a bar graph in which you have taken these nominal or ordinal categories and you basically have shifted them around. So ordinal basically is now ordered, but not ordered anymore in the way that's actually nominal. So you take the highest one and you are basically the one with the highest y, and you're basically reorganizing the entire thing. So if we have here the percentage of internet users who also use Twitter, interestingly, Indonesia seems to be very Twitter friendly, and so is Brazil, which I didn't know. A lot of friends from Brazil who are also on Twitter, it's true. But essentially, it wouldn't be my first guess. Okay, but you have Twitter being quite popular here, with Venezuela, Brazil, and Indonesia being the leading, whereas the UK and Argentina and Turkey low on Twitter. Interesting. All right, so standard bar graph. You see you see here a nominal x-axis, a scale y-axis. The Pareto chart reorganizing all bars in a descending fashion, where basically the highest y is on the very left, the lowest y is on the very right. So now, this is the difference between bar chart and Pareto chart. So now, let's go further. Okay, bar graphs can be misused. Bar graphs highlight differences between averages or percentages. So now, I don't know how if many of you know this project is that basically people would be labeled as ex-prisoners if they had a tattoo. So essentially, you can mislead this graph. By essentially rearranging the bars. So now you have no tattoos, percentage of people who have been arrested at least once. With no tattoos, low number. 1 tattoo, higher number. 2 to 3 tattoos, lower number. 4 tattoos, actually the highest probability of being arrested at least once. So now, does that mean that people with more tattoos are more likely to have been arrested once? No, absolutely does not. And that's the problem. That's the problem with a lot of analyses, right? If you would like to make a statement like that, you essentially need an extremely high case number. You need to query and survey a lot of people to essentially make sure that you are not giving out misleading information, because you don't have a marker of variability. So it's like, I don't think that tattoos is necessarily a predictor of going to jail. But again, are people that are in jail more likely to have tattoos? Yeah, I could buy that. But it's a different level of looking at it, right? It's a whole different interpretation. So you need to understand, how are you looking at things, and what do things actually really mean? But this is what I want you to always keep in mind. It's like, think of exposure and outcome. Exposure being having a tattoo. Outcome being in jail or having been to jail. So you got to make sure that you are understanding in what sequence you're looking at things, because this analysis here without having variability, I'm not buying it. Particularly not like that, because now you essentially you're going even further and you're offsetting the axis. That makes it even worse, because now you're essentially, you are taking this, which is like really low, this, and this. You are basically inflating the association tremendously by making this even more impressive as a difference, right? And this is just, it's really deceiving when you play around with the scales. And this is important to keep in mind. And you will see a lot of these scales, particularly in magazines and newspapers. You see a lot of these scales. It's actually really, really bad. Just keep it in mind. So pictorial graphs. This is also quite a complicated topic, because it's also very, very popular. Magazines, journals, newspapers, super, super popular. So you're choosing clarity over cleverness. So you essentially would need to choose a clear depiction to make sure that you're really not misleading with whatever you're showing. So you provide a visual depiction of data for an independent variable when there are only a few levels and a scale-dependent variable. And the problem why this makes sense is because you need to make sure that you're not deceiving with your pictures. So if you're distorting data with pictures and you make a graph like that, you essentially you are, yeah, you're basically, this is non-scientific graph. This is a cartoon at best. So absolutely no go. Same with pie chart. It's like, I don't know who came up with the idea of a pie chart, but like it's just not, it's not intuitive, right? It's just absolutely not intuitive. It's like I'm not a pure statistician, but I know the statisticians hate pie charts even more than I do. It's like it's a non-informative graph because you don't get much information from it rather than a visual kind of representation of what you're looking at. So if you do, so pie chart is basically a graph in the shape of a circle with a slice for every level category. So, but you can't really distinguish the size of each pie, pie piece of pie. Because the size of each slice represent the proportion, but if you don't write the proportion on there, you have no idea how much the proportion is. Like, you're not that good in guessing the circumference or the part of the circumference, the partial circumference. You're not that good. So it really requires an extra layer of labeling, and that just makes it absolutely useless. So, but yeah, judge by yourself. It's like, if you look at these two pies, how easy is it to actually compare this? It's like, you need to read the percent. And if I have to read the percentage, like, why do I need the pie? I don't need the pie. It's like, you can give me that on a table, it's the same effect, right? Despite of that, these slides are kind of interesting anyways. So yeah, so that's just a funny pie as well. Okay, so but yeah, it definitely does not make much sense to depict data in a pie chart. A better way to depict data that goes in a pie chart, percentages for each nominal category, is to use a bar graph. It's a much more elegant way to actually depict data. It's a much more elegant way to actually get your message across and to make your case. So I highly recommend that instead of making pie charts. So choosing graphs based on variables. Okay, so this is the most important slide of this slide deck, I find personally, because this is where you basically, and I'm flagging this for the quizzes. Make sure that you have understood each of the graph types and that you know which one is used for which indication. So if you have one scale variable, you either use a histogram or a frequency polygon. Histogram, you remember, is like a bar chart with bins of a continuous x-axis, and you use this bins, and you count within that bin, within that range on the x-axis, you count the occurrence of each value. And the same you do with a frequency polygon. Frequency polygon is nothing else but taking the top point of this bar and connecting these and then smoothing it out a bit. So it can be either like from one bar to another top, from one bar to another bar, top of another bar, or it can be smoothed out and can go smooth up and down. Another way to depict data is if you have one scale independent and one scale dependent variable, you do a scatter plot or a line graph. Line graph, and I'm flagging this, scatter plot, independent values. Line graph, you need a dependency between each line. So this is for the sake of simplicity at this point, line graphs only when you look at time series. And I think you get away with this for the test. Don't use line graphs if you don't have a time dependency. Use the scatter plot instead. If they're independent, scatter plot, not line graph. If you have one nominal or ordinal independent variable and one scale dependent variable, you use a bar graph, or for nominal, you can also use a Pareto chart. If it makes sense to depict it in the way, if you want to see whether Venezuela and Brazil use Twitter as often as Indonesia, you use a Pareto chart. Two or more nominal or ordinal independent variables and one interval dependent variable, we're again back at the bar graph. So interval, don't forget, interval ratio meaning for 0, time cookies, number of cookies, interval, temperature of cookies. So think along these lines. Equally spaced, no meaningful zero, can also be negative. Ratio, meaningful zero, there's no negative number of cookies. Well, you could owe cookies in, well, now you don't owe cookies. So if there are no cookies, there are no cookies. We don't do negative cookies. Okay, how to read a graph? So there are a couple of questions that you need to think of. So firstly, you need to understand which variables are the researchers actually trying to predict. What is the dependent variable? What is the independent variable? Is the dependent variable on the y-axis really a dependent variable that is important, interesting in the context of the research question? Is the independent variable really important and really what you think it is? Then, is the dependent variable nominal, ordinal, or scale? Because that changes which graph you're going to use. You don't want to have an ordinal Pareto graph, right? Doesn't make any sense. Because then you have rank 7 is suddenly your first on the very left. This is misleading on its own right. Understand which variables you're looking at. What are the units of measurement? That is important because you may see relationships when you have a certain unit, but once you change the unit and you look at a different unit, you may not see this relationship anymore. Also, which variables did the researchers use? But that's just what are the independence variables. But that is a general question for all research questions and all research and hypothesis testing approaches that you use. So this is kind of always the case. Then also, are these two independent variables nominal, ordinal, or scale? You need to understand that. You need to know that. And what are the levels that we're actually looking at? So really go through this list when you're being asked to interpret the graph. That's very important. So, guidelines. So what do you want to do? Graphs. Don't mesh them up with like a million things. It's like if you, those of you that are analytically inclined, that are planning to go to some extent into data analytics or somewhere close to that, you will likely work with different softwares, and there are softwares out there that are more likely to actually use very, very colorful graphs and very packed graphs with like a million different analyses. Don't do it. Don't use it. Try to keep them simple, clear, with a specific title. Label the axis with variable names that are kind of readable and not like abbreviations or acronyms. Also, if you have a scale-dependent variable with a unit, I highly, highly recommend and I encourage you to always put the unit on your axis label. The compatibility of terms of the graph and then the text, that means that what the graph shows, the text should represent the same thing. If the text talks about a different graph, this needs to correspond, right? Makes a lot of sense. Inclusion of units of measurement, yeah, I just talked about this. Always label it on the X or Y axis. Make sure your axes are labeled correctly. Values should always go to 0 or predefined cut marks. If it doesn't go there, find a reason why it doesn't go there. A scatter plot, for example, is really, really misleading. If it doesn't go to 0 on both Y and X axis, it's very misleading. Keep that in mind, please. Careful with color coding. Careful with colors and don't put in chart chunk. So what is chart chunk, you're going to ask? Chart chunk is unnecessary information or features in a graph that distracts from the usability to understand the data. There could be more array vibrations, grid, and ducks. So we will see what these are. Computer-generated graphing problems will be the solution to that, but they also are misleading because they allow for you to do and to add all this chunky kind of additions. So be careful when you use graphing programs, be sensible about it. So there should be a lot of information in there, but there should also not be too much information in there. And we will see good example and not so good example. So this, for example, is a bad example. So this is a chart chunk. So firstly, we have here So these patterns, these patterns are called the Moiré operations. They are like, don't use them. Absolutely don't use them. So I highly discourage you to use them at all. So I really would not. And so then we have the chart trunk. So this is, I believe this is a duck, which is not serving any purpose. So I would definitely leave that out. So definitely not helpful. The future of graphs, interactive graphing. And this is an interesting topic. This is a very interesting topic, and R and Python do have interesting solutions, and there are other solutions out there where you can have graphs that are interactive. You can turn them, you can look at them from different angles, and maybe something that may be able to be embraced at one point. I could see that. I could really see that. The problem is it will take time, and it likely will not be tomorrow. Reason for that is that at this point in time, you cannot show them in a journal. You could have add them as online supplementary material. That's a possibility. That's definitely possible. But it's not very intuitive. It's not really an easy sell. So you would still need to find an editor who would be leaning into doing that. If I were the handling editor, yes, I would be leaning into it. It would probably cause some extra work because the editorial office is not going to be happy, but yeah, you may get it in. But I think it makes a lot of sense to kind of keep it in mind and keep an open mind for it. It may come through at one point. Then we have computerized mapping. So this is new. So there are, in the meanwhile, and those of you who further the information education analytically in some shape or form. So I did, for example, I did, that's funny background story. So my professor from that class, so that was in environmental population health. So we actually did program ArcGIS, which is a geographic information system where you map out incidence rates of a certain disease all over the maps of the entire world or a certain region. My professor, actually, who was my professor back then, is now a co-lecturer of mine at CUNY. So I'm teaching a class at CUNY, a graduate class at CUNY, and he's a co-lecturer of mine. It's kind of interesting. It's funny. Very nice colleague. And so he taught us how to use those, and it's phenomenal what you can do with these tools and what you actually can do with the tools that are currently free of charge, open source available. So it's right now we are really on to a new age, a new era where you don't have to pay $20,000 anymore to get access and get a license for a super expensive software. No, you get open source software, and you can just get wonderful things, just wonderful software, wonderful tools that allow for you to really do a state-of-the-art job in terms of analysis, in terms of programming. So it's really very nice. The future of graph, clinical applications. This world has opened up. It's like I come from a world of dialysis. You basically have clinics and units where nephrologists walk with an iPad, and they're connected to the database. They can graph out analytic processes. They can graph out dynamics of lab parameters and clinical parameters. So these things are happening. These things do exist already. So you will, if you go into medicine and psychology, by the time you're finished, this will be your daily bread. I guarantee you that you will see a lot of graphs. So take this serious what I'm telling you. This is really, it's going to be very important. Then we have word clouds. I guess you all have seen word clouds, right? It's like it's basically like you see these different words. It's like those words that have been most often cited in a survey or in a feedback, provided feedback by attendees, and things like that. They are going to be bigger, and so the size represents the number of how often that word has been mentioned. It's a nice way to depict, but it's more on a marketing kind of thing. So it's not really analytical. Analytically, you would use different ways of depicting that data. All right, what else we got? So we have now multivariable graphs. Yes. So this is one that Nolan and Heinz have included here, so-called bubble graph. You will see my hero, Hans Rosling, population health expert, showing bubble graphs on his own analysis. He's just as fabulous. And he's using this bubble graphs at the really highest level. This is the one that Nolan and Heinz has shown, more psychologically inclined, less the topics than those that Rosling shows. Positive emotions, we have here different color coding, which we don't know what it is, but true. Yeah, the color represents the GDP of the country. So red seems to be a low GDP because Georgia and Armenia are definitely not heavy hitters in terms of GDP, whereas Ireland, Switzerland probably more so. So the So the lower the GDP, the lower the self-reported health, which is not entirely surprising. The lower the positive emotions, and the higher the GDP, with yellow being high GDPs, the higher the positive emotions and the higher the self-reported health. Why Georgia is that low? I'm not entirely sure. Georgia, I think, is an economically quite improving country, but I'm maybe missing something there. Interesting about the countries that I know: United States and Switzerland. Right next to each other, Australia is slightly higher in terms of positive emotions. The happiest seem to be the Irish. Interesting. Okay, so but it's an interesting graph, right? And so this is an interesting way to look at data, and you get a third dimension. So you have a scatter plot. So you have a discontinuous scale, which is a no-no. But you basically have a bivariate graph. So you have self-reported health, you have positive emotions, and you have GDP as a third dimension, which is a nice way to go about it. And you will see the Rosling graph. And we have done, what we have done is also interesting. So we did quote unquote contour plots, right? So you can, if you have this bivariate kind of setting and you have a more continuous scale and you don't have like only points, so, but you have regions, you can actually map this out like a topographical map. Like you look at a map and you see like elevations on your map. You can do the same thing and you can color code these elevations. So we did it for risk of death with some various bivariate associations. Is another way of doing that. So there are various ways out there. Then we have uncovering hidden stories by displaying variability. So what they mean to show here is that it's always important to kind of show data and to show raw data. So you can hypothetically, if you have outliers, so this is called an outlier. These outliers are, for example, taken by a bar graph, incorporated, and you don't see them anymore. So this outlier could mean something, but you don't know. And you don't know what it means. And you don't see it anymore. And that's a problem, right? because that data point could really contain a lot of important information, and it's important to see the dynamic and variability. So this is why there always should be marker variability, and we will talk about this during next class, beginning of October. So keep all of this in mind, and please rewatch this before we actually get into class. So a lot of different information do play a lot of role here. Like, so outliers are not being depicted here in bar graphs. Different sample sizes not visible here in bar graphs. So you only see the mean, which is somewhere where the bulk of the data is, but you don't see what the actual underlying dynamic is. And that's a problem. And this is why depictions like that, and one of my favorite graphs is actually not shown, which is a so-called box plot. So a box plot is actually a graph that will show you this here in the middle only. Oh, sorry. Will only show you this in the middle, and will show you here the box, which is here the median. This is the middle score. Then you have the middle 50%. Then you have 95% of the scores shown here in that entire span width, and is a very elegant way to show. But what this actually is the so-called Violin Block, and the Violin Block essentially is also interesting because the Violin Block shows essentially the distribution of data. So you remember how we looked into the normal distribution, right? So the Violin Block essentially, if you tilt it around, you actually see the distribution, just like in a frequency polygon or in a histogram. And this is actually quite helpful because here you, for example, you see that this data is left skewed. This data is left skewed because the bulk of the, it's actually right skewed because the outliers are actually to the right, which means that mean and, oh no, we didn't talk about this, but mean and median are actually going to be different. So the mean is actually going to be here, whereas the median is actually here. So this is a very important and interesting insight. So there's clearly differences along the lines of distribution. So this actually is a very insightful graph. And this is basically what I had in terms of slides. So this is the Violin Block. Very interesting graph, I think. And I have actually used it in various situations in my analytical day-to-day job. And so now we're going essentially quickly to our lab. So we're gonna do a quick kind of lab situation. Hold on. This and this. Okay. So this is, I'm just gonna quickly, I'm gonna post this. I'm gonna post this obviously, that you have it at your disposition. You can play around with it. So we have here I'm going to save this here. So again, I hope you all have this folder that I asked you to produce. So I think it's very important that you have stat 1021G, module 3, no, module 4, right? Module 4, right? Yeah. So I really want you to save all the work we're doing here in that folder. So create a folder, please, on the desktop, the step 1021G, create a module-specific folder and save your data in that module-specific folder. I think that's really important, and I think it should be part of the outcome of this class. That you have a couple of Excel examples, that you have a couple of R codes, and I think this makes a lot of sense. So most commonly you will be using most commonly you will be using data from that will be imported into Excel. So You may never use R, but you certainly will use Excel. There's just no doubt that you will. So Excel and scatterplot in Excel is actually very easily done. So you just select the data frame, you go and insert, you basically go on insert, you go on the respective graph, you pick scatter, and tada, that's already it. So that's here. This is the data for athletic performance and hours of deliberative practice. You remember this one? This was this data. So I have gone through that data and I have digitalized this data for you. And so now we can play around with it. So this is the same graph. So now this is athletic performance. Oh, come on, athletic performance. Athletic performance. And practice. So now once you have this in, now you can just select the graph, you go on format. So you can add a chart element. So chart element would be, for example, trend line. You can fit a linear trend line. Ta-da. Now we can go on format. And we can format pane. So here we can do various things. We can use here chart design. We can also go on add chart element, axis titles, primary horizontal. So this is now hours of deliberative practice. Hours. Now we can do axis titles, primary vertically. We can do that performance. Cool. Okay. And that would be our graph, right? Looks like this. So this is this way how to do that, right? And that was simple. It's not complicated. And it's the same in R. So now forget about this. So this is essentially, this first line is emptying the environment. This is just how to set up the data frame. It's really this that counts. And plot df hours and df AP is essentially how you can plot this data out in R. There are a couple of additions that you can make now, where you can actually say xlab. Xlab is the label for the x-axis, which is hours of deliberative practice. Hours. And then ylab is athletic performance. Athletic performance. That's cool. Now basically looks the same, right? Now we want to have an airplane, which is, yeah, it's a little bit more complicated. So this is not that easy. So airplane would be LM df as a function of df, and we will teach you within that. But this is basically, this is your line. Now we can also include main trans what did we say here? This. All right. So this is our graph. Some more. Where's it? Where did it go? Oh, there it is. Okay, athletic performance and practice in R and Excel. Simple, right? Not a problem at all. All right, and this is pretty much all I had for today. And I hope it wasn't too bad. I hope you had a good start of the new year. I wish you a good break, great holidays, wonderful time with your families. And I see you back beginning of October. And please don't forget about statistics. Watch this video, rewatch the other videos. I really, in October, given the midterms are coming fast, we need to hit running ground because I want to review with you guys. Please do the sample quizzes, practice, and try to keep a pace with what we did so far. It's not that much, but what we did will it will increase quite frequently, quite rapidly. Sorry. All right, good. Have a great time, and I see you very soon. Bye-bye.